you get so spoiled with that whole I can't remember how it used to say that. That's awesome.
I've never used it before. Squid.
I haven't used it a lot because I usually use an IE.
Which I don't.
Well, at work I usually use Visual Studio.
I downloaded it before. But they don't. That doesn't have to see, is that right?
Yeah.
It does?
Change all video.
I mean, it compiles it to C++, but you can write straight C code in.
Change some any.
I missed that. Right. I don't include it because I was like trying to use that for something.
You must have, yeah. So I have
So it's Visual C++, Visual Studio C++.
I have a full version too, so it's got like C, C sharp.
You can only start with just the student version.
All right. Well, let's go ahead and get started. So how was the previous homework assignment, Socket 2? Is it kind of okay?
Yeah.
It works.
It works.
I was having one problem where I couldn't, my client could read into file and it would write into file just fine, but by the time the server got into file, something was wrong and it was returning -1 on read when it tried to read into file, and I checked the error num and it was like client peer close the connection or whatever. So instead, when I read into file,
Did you pipe in a file to one of the clients? Did you use the redirection? How did you test your program?
I just with full functionality as far as the server and client talking to each other.
Okay.
And so once the client tried to send, when it tried to write into file, it would read into file and it would write into file because I checked what are you writing and it was into file. But then by the time it got to the server,
but you don't write in a file. You don't write Control D. It's just automatic. When you terminate a connection, it automatically sends in a file. End of file is a condition, it's not a character.
Oh, okay, so when the client reads into file, all it has to do is close down?
That's the description of Socket 2.
Okay.
Yep. When the client sees end of file from standard in, then it has nothing else to do, and then they should close the connection.
So you don't write into file to the server?
No.
Okay. I always try to make things more complicated.
Well, the concept of end of file is a little bit confusing because when you interact with a program, when we specify end of file, we type Control D.
Right.
So that's why a lot of people associate, Control D as quote unquote the end of file character. But that really is not the case. It's nothing more than just like Control H is the backspace character.
Okay.
In other words, Control D is just a way to tell your program that I'm done. That your standard in should close now. But when you're redirecting from a file, using the less than symbol, then when the program finishes reading the entire file, there's no Control D at the very end.
There's no end of file character?
There's no end of file character.
There's a null character?
No, there's nothing. Because if you remember from the inode discussion, the inode knows how many bytes each file has.
Okay.
So when the file descriptor or the data structure in the operating system recognize that you are reading to that point, that you have already read the last byte in the file, it will automatically make read return a 0 to indicate, hey, there's no more byte to read anymore, and that will be the end of it.
Got it.
Okay. All right. So let's go ahead and get started with Socket 3. For those of you who cannot finish Socket 2, you can use my code. There's a Socket 2. I just have to put the link back up again. But let's go ahead and take a look at Socket 3. Some of you have already gotten started with Socket 3 already, and but anyway, I'll just start from scratch. So to set up Socket 3, log into an account that is based on your name so that I can grade and I know who turned in. Create a folder called exam2. I know this is not your exam, but go ahead and just use the name anyway. And you can choose to use your own Socket 2 program from the previous assignment. And in that case, you will have to first handle the pipe signal so your server code won't terminate when writing to a socket that is already closed by the client. Because sometimes in this particular program, that can happen. And we have already started to talk about signals. So are there any questions about signals? No? Okay, not yet. Okay, so I'll just go ahead and skip to the behavior of the program so that we understand what the program is supposed to do. change the program to time out the server broadcast write calls. In other words, it's only the write portion of the server that needs to have a timeout mechanism. The read part does not. Okay, that means, as a server, let's say I'm the server, when I'm waiting for clients to send me something, I don't need to time out. The clients, all 3 clients can take as long as they want to send me something. The only time I want to time out, is to say, okay, I'm writing back to the clients. Okay, let's say somebody sent me a byte. Okay, and as a server, my job is to broadcast that byte to all 3 clients. So when I'm broadcasting that byte to the 3 clients, I will time myself. Okay, on all sockets that I'm supposed to be writing to. I'm not selecting on one single socket at a time. I'll be selecting on all 3 sockets, at first. Okay, so let's just say that the 3 of you are my clients. So I will do a select call on write to all 3 sockets. And let's say the 2 of you is taking my byte right away. So my select call is going to unblock, and based on the write set that I get back from my select call, I know that you can receive 1 byte. So I write 1 to you, and you can receive a byte and write 1 to you. But you did not tell me that you're ready to write. So that bit, I still have to go back to the select call again to wait only on you. Okay? And that's where the timeout comes in, is when I'm selecting on write. So if you do not take my byte within whatever amount of time I specify here, then I'll time out. So that means we can now go back to the instruction and figure out, okay, it's 10 seconds. Now for testing purposes, you reduce the amount of time to, let's say, 2 seconds, because 10 seconds is a long time. I mean, you can just cut it down to 2 seconds to test your program more easily. If a connection is not ready and timed out, report the error as server cannot broadcast to file descriptor X, X being a number of the actual file descriptor, and the timeout connection will lose this particular character. Now this means, if I am writing, let's say, a character, and one particular client times out and say, okay, I'm not ready to take that byte, that particular client will just miss out that byte. Because when the select call comes back and say that, okay, we just timed out, this client was not ready to be written to, I'm just going to move on. Right? All right? You also have to write the logic to see if a particular client has timed out 3 consecutive times. Now, what do I mean by 3 consecutive times? If a client times out 1 time and then the next time will take the byte without timing out, then I have to reset the 3-time timer. I mean the counter, because I have to reset it back to 3 because then. I'll put it this way. In terms of logic, the best way to look at this is if a particular client does not time out, reset the counter to 3. If a client does time out, take 1 out, reduce the counter by 1. When the counter gets down to 0, then that particular client is considered extremely tardy, and you basically terminate the connection to that particular client. Are there any questions about this? No? Okay. So closing the connection will cause the client to report an error. That's fine. Let the client complain. The complaint has to do with you're closing a connection, and the client is still trying to read from the connection, and so it's going to have a little bit of complaint. To test this feature, use 4-party terminals in Windows. You can also watch the video here. So how many people have watched it? No? I haven't watched it for a while too. Oh, I guess it's silent, but it's captioned. here comes the third time. If you guys have any questions about the clip, let me know. But I think it's here, and you can actually slow it down or even pause it so that you can read the message that I'm typing here. But it's a demonstration of how to test your program. How do you test the timeout, and how do you set it up? In this particular case, I use multiple tabs of the same terminal, so this way I don't have to flip through different terminals, because that would be more distracting. To open up a new tab on your terminal, you just either use File and then say Open Tab, or if you know the shortcut key is, I think it's Control-Shift-T to open up a new tab. It's a really cool feature because you don't have to open up multiple terminals, which is really harder to navigate than having to click on just the tabs. Yep.
Is there a shortcut key to cycle through?
Yes, I cannot remember what it is, but yes, there's a way to do it.
I think it's just
Control page down and control page up.
Sorry?
Control page down and control page up.
Oh, control page down. Yep, there you go.
Okay.
And you can also use Alt and the tab number that you want to go to. If you want
Okay.
to go to
Alt 2, Alt 3. All right, excellent. Very good. So any questions about how to test your Socket 3 program? Questions? Now I remember why this is silent, because it was a question in an exam. So I didn't want people to have to plug in a headphone to listen to the instruction. So I made this video clip completely silent and use the text to annotate what I'm doing here, so that people can follow the instructions during the exam. I thought it was a very fair exam, but the class did not think so. I think with this type of programming practical exam, the problem is people may be able to get the concepts, but they cannot get the program to work within the allocated amount of time. And I think the pressure also get to some people. Some people just cannot function as well when they're under pressure. If I did not say this was an exam, some people may have been able to finish it, but as soon as it counts in an exam, some people just kind of shut down and go like, no, I cannot do this. But out there in the workplace, sometimes it's even worse. You have deadlines to meet. And it's not just an exam. It's not like 20% of your final grade that is, that is being affected. It's the actual employment that is being affected in that case. All right. So the instructions are here too. I'm just writing out the instructions of how to test the program. Start the server. Just like you usually do with Socket 2. Start the first client normally, and then you press Control-S, which basically stops standard out from spewing stuff out. Start the second client normally, and then press Control-S to pause it. Start the third client by redirecting its input from socket2.c, and then start timing. Because it will almost start to block immediately in this case, because both clients cannot be written to. Then you want to switch back to the server and wait. After 10 seconds, the server should complain that both client 1 and client 2 are timing out, because you did a Control-S on both, okay, and it will just block. It will take about 10 seconds to simultaneously time out both client 1 and client 2, not a total of 20 seconds. And then quickly, you switch back to client 1 and then press Control-Q, and that resumes the output to standard out, and therefore it will not block anymore. But don't do this to client 2, because we want client 2 to time out. Client 1 should now continue to get broadcast characters. Switch back to the server. After another 10 seconds, the server should only complain that client 2 times out again. After another 10 seconds, client 2 will time out one last time, because that will be the third consecutive timeout. And then this time, the server should terminate this particular connection because of the consecutive timeouts. Client 3 should exit after an encounter and a file of socket 2, the file itself, and then client 1 should get the rest of socket 2, and then continue to operate as the only client left connected to the server. So this description should be before you start on the project, you should definitely understand the description. This particular scenario is very important. Because if you don't understand the scenario, what this script is testing, you should ask questions, what the program is supposed to do. Are there any questions about the program itself? It's for the most part, yeah, go ahead.
We got client 3 is the one that's sending that information, right?
Correct. In this particular case, client 3 is the one that is originating the content.
So the EOF that's encountering is just when it's done with the file, you're redirecting it?
Say again?
Is that what's the EOF that it's encountering that closes it? It's the end of the file you're redirecting?
Yes. Because you're redirecting from a file, so once you unblock client 1 and client 2, excuse me, I take it back. Once you unblock client 1 and client 2 dies, then the server will be able to read everything, and then the client 3 will have nothing to feed the server at some point because the input file will encounter the end of file. So at that point, client 3 will exit normally because it says, whatever I'm reading, I have read everything already. I have nothing else to do. So it will close its connection just like with socket 2, because in socket 2, when the client encounters end of file, it would also terminate. So that part should not require any additional code or additional logic to handle. Any other questions about this? Yep.
I'm not quite clear on the redirecting the third client to socket 2.c. That's different than just starting it up in client mode.
Start it up in client mode and then use a less than symbol to redirect from a file.
For just any file?
Well, I use socket 2 because it's big enough to make sure that it will clog the pipe.
Oh, I see. Okay.
It's not pipe, in the pipe it's the socket.
Okay.
Yeah. Any questions about this homework assignment? No questions? Okay, I'll put the link to my socket 2 solution back up again. I don't think it has the same solution to the bidirectional pump that I did on the Wednesday before the break. So let's just go there one last time. So I want to show you, where that program is, and not sure whether I have uploaded that or not. Did I upload that program? The one that I did before the break? Did someone ask me to upload? I guess not.
You just put up the files. You just put up the YouTube videos.
Okay. So what I can do is I can upload a file today. Let me go back there. What is the Wednesday before the break?
The 28th?
The 28th? Yep. And bidirectional pump is the program. Okay, so I can upload this too. So let's see. By the way, I told some of you already in the lab, the chancellor of the entire community college district has arranged a meeting with people on campus on Thursday to talk about the 2012 to 13 budget situation. Do you think it's going to be good news? Like, oh, we got lots of money now. Let's think about how to spend all that money.
Is American River offering summer classes?
We are, but our summer schedule is going to be very impacted because of the mid-year cut. That's basically what he's here to talk about, is the mid-year cut. We have already made preparations as a college district. We have already made preparations for the worst. So we are not going to be impacted as much as other community colleges. But we are still talking about the 25%, at least the 25% reduction of summer classes. So there will be summer classes, it's just not a whole lot.
Yeah, the catalog is out. Is that catalog going to be correct, or are they going to be cut?
That will be the correct catalog. I think that's with the cuts already, included.
Yeah, there's no CISP stuff.
Well, the other thing is we cannot really, at this point, we cannot cut classes in the fall either, because all that stuff is already being scheduled. Even though do you guys have the fall schedule now or not? Not yet.
fall schedule won't come out until like July.
Okay, but that stuff is not going to change either. So that means that the mid-year cut that should have affected the fall 2012 is not going to affect 2012 fall. And next spring, 2013 spring, we'll have the combined cut of that year as well as the mid-year cut of this year.
The fall schedule was out.
The fall schedule is out?
Yeah.
Okay, so you can expect 2013 spring to be a really bad semester to get classes because it has to absorb, the mid-year cut in addition to cuts that are intended for next year. And this district is already doing fairly well, all things considered.
Yeah, our community college isn't having summer classes.
They are?
They're not. In
Oh,
Fairfield,
none?
Solano, they're closing the whole campus down for the summer.
Yikes.
And that affects, our whole community. There's high school kids that count on certain things because, we have an IB program.
Mm-hmm.
And they count on being able to do certain things at the community college, and now they won't be able to. It's a mess.
It's a mess. It's not helping the situation either because all this is doing is delaying people getting out of college and getting a job and start to become taxpayers.
Yeah.
And Sac State's threatening to not let anybody in fall of 2013. They said maybe some transfer students, but probably no incoming freshmen.
Wow. Did you guys hear that?
Yeah, fall and spring. They're doing it for both of them now.
Yeah.
Now, is
So
Sac
spring
State-
had already started, but fall 2013 they're saying.
Wow.
Oh, yeah, spring 2013 is well now.
Yeah.
But that is bad because that means their pipe is going to run empty because they have no incoming freshmen.
Well,
So at
because they
some
need
point,
to cut enrollment, so that's what they're doing.
Maybe reduce it, not just stop it.
yeah.
But they don't send a message if they quietly reduce it. They're trying to send a message to
Yeah.
the public and to the legislature.
Yeah.
Yeah, right. I don't know what to say.
We're screwed.
All right. So this is my pump. The program name is called bidir pump. Bidirectional pump. So you can borrow this code if you want to. You can integrate this code into your next program. This is basically what your client is supposed to do, except your client is not going to use pipes. It's going to use sockets. So I think anyone who understands up to this point what we have been doing should be able to integrate this program into your own if you want to use this particular bidirectional pump. The bidirectional pump, as I explained last time, has to do with not blocking unnecessarily. That's basically what this program is all about, is not blocking unnecessarily. Because you have a two-way communication, you have a two-way pump. In other words, you have two independent pumps. One pump is pumping from server content to your standard out, and the other one is pumping from your standard in to the server. And these two directions should be completely independent. In other words, even though the server says, hey, stop, I cannot talk to you anymore, I cannot receive another byte from you anymore, if the server has content to send back to you, you should still be receiving those bytes and displaying those bytes on standard out. And the vice versa part is true as well. Even though you're waiting on the server and the server has nothing to transmit to you, that should not stop you from reading standard in and transmit stuff to the server. So that's what this program is about, is basically saying that we are not going to block unnecessarily. Anything that I can do, I will do. Okay. So you might want to take a look at this program. Since it is already on the web, that means you can use the program if you want to, or integrate part of the logic into your own programs. Any questions about the bidirectional pump program? We talked about that the other day, and it's a little bit complicated because it's a state machine thing, but I try my best to contain the code so that it is more modular, and you can basically run it using a more modular fashion. Yep.
Would we ever be worried about Select saying that there's something available to be read, and then by the time we read it, it's not available for some reason? Was that?
That is always possible.
Yeah.
The one thing that I do not know for sure, whether how it's going to happen, I guess I can write an experiment to do it, is this. Okay, you run the server, you run the first client normally, you run the second client redirecting a small file to it. Okay, it has to be small, cannot be big. You redirect a small file to the second client. Now what will happen is the server will connect to the first client in the first loop, and then it will connect to the second client. As soon as your server connects to the second client will get through its own connect call, and then will get into its own pump. But because we are redirecting from a small file, it will be able to read everything in the file in standard in and transmit everything quote unquote to the server, because the file itself is smaller than the capacity of the buffer going to the server. So your second client is going to terminate like right away. But your server doesn't pay attention at that point because it's waiting for the third client to connect. So let's say you run the client the third time, so now you have the third client, but the second client is gone already. So by the time you get into the broadcast mode, you'll be reading from the socket coming from the second client, and I think the reading part will still work because there's still stuff stored in the buffer for that particular socket. So the server should still be able to read from that socket that belonged to a client that now has terminated. The problem is when you try to echo, when you try to broadcast the characters, that will have a problem because that pipe is now broken. Okay, is that okay?
But you'll get an error of some ilk.
You will get I think you get a SIG pipe, the signal pipe, problem, and that's why in the homework assignment, the first thing you want to do when you read the homework assignment here, the first thing you want to do is to handle the SIG pipe, signal, to basically ignore it.
And your socket 2 does that?
My socket 2 does that already.
So you have the first client connect and send it the little file real quick, and then you would connect to the second one.
You should not do that because it doesn't really test your program that way. So you should always be transmitting redirecting from a file that is larger than the capacity of the buffer itself. Let me just make sure that I create that link too. So I'll go link to a file. X socket 2 solution. It's not a perfect solution because I did not actually integrate my own bidirectional pump into this one, so it does block sometimes when it doesn't need to block. And it's called socket 2. What is it? I will have to find it. Right now, I don't know where it is. Maybe socket 3.
You can give us the next one now.
I knew somebody's going to ask. Nope, that's not the one. All right. I cannot remember where I put it. There was a link before, I just have to. Oh, there, right there, socket 2. Yep, there we go. There we go. So now you have socket 2 and also the bidirectional pump. You should probably, integrate those two because, my original socket 2 does not have the proper bidirectional pump. It does block sometimes unnecessarily. Any questions at this point? Yep. Go ahead.
Just to help me with the concepts, why does the bidirectional pump help to not block unnecessarily? Is it because of the state?
No, because of, well, let's take a look at socket 2 first. Okay, this is my own socket 2 solution, and it even says so. The program uses a lazy approach. The server selects is based on this client incoming connection. When select returns, the server scans through all incoming connections with something available, and so on and so forth. It appears to work, but it can lead to excessive blocking. So, it's not using select effectively, but it does work. And it's also not fair because someone can hog the server. But for the purpose of this homework assignment, it's still okay because the timing out part does not rely on being fair. And also selecting as little as possible. So this program does work, and if you look for signal, this is the signal part here. This is something that we have already started to talk about, not finished yet. And what this does is when it receives a SIG pipe, I'm telling it to ignore it. The default operation for SIG pipe, when you're trying to write to a file descriptor that has been closed on the other side already, the default operation is to close the program, to terminate the program. But you don't want that because you basically just want to say, okay, we're going to kill that client at some point. It also has SIG kill is also going to be ignored, and SIG int is also ignored. Some of these signals cannot be ignored, but it is just doing that in this program. Yep.
And the man page of Signal, it said not to use Signal, but to use SIG action.
Yes, very good. Okay, so let's talk about that. Okay, very good. I'm glad that you guys are reading the man pages. Okay, in the man pages, it says avoid its use. In other words, avoid the use of signal, the function signal itself. Use SIG action instead. And the problem has to do with portability. In other words, what you can do with signal in this particular, the behavior of signal in Linux can be different from the behavior of signal in other operating systems. So we'll go ahead and take a look at portability, which is down here. Right here. Portability. The only portable use of signal is to set a signal's disposition to either default or ignore. Now, in this particular program, we only set the signal to ignore, so we are fine in this particular case. The semantics, or the meaning, when using signal to establish a signal handler, in other words, something other than default or ignore, vary across platforms, and POSIX 1.1 explicitly permits this variation. Do not use it for this purpose. In other words, do not use signal to specify how to handle a particular signal other than default or the ignore options. POSIX 1 solved the portability mess by specifying SIG action. In other words, they recognize there's a problem. There are different ways of doing the same thing, and they use SIG action to basically fix the problem because it is a more unified approach, which provides explicit control of the semantics when a signal handler is invoked. Use that interface instead of signal. And then it goes on to try to explain what the current problem is. In the original Unix systems, when a handler that was establishing using signal was invoked by the delivery of a signal, the disposition of this signal would be reset to signal default. Okay, so let's try to read this sentence again and figure out what it means. I already know what it means, but it's a really long sentence. Programmers do not write sentences in a well-structured, concise way. It's just like writing a program, right? In the original Unix system, when a handler that was established using signal was invoked by the delivery of a signal. Okay, so let's just read this part here. The disposition of the signal will be reset to SIG default. So that means right after the delivery of a signal, it will turn itself back to the default. Okay, so let's just say that I'm a process. Okay, I want to handle a particular signal. Let's say SIG pipe. Okay, just for the discussion. So I will say signal and then specify SIG pipe, and I will specify a function to handle SIG pipe. Okay, and then I'll just go about doing my normal business, reading and writing and stuff like that. At some point, let's say I write to a pipe that is already disconnected from the other side. So SIG pipe is going to happen at that point. SIG pipe happens, I will get into the signal handler that I have established already. But what happens after I return from my SIG pipe handler? This says that it will go back to the default operation. In this case, the default operation for SIG pipe is to terminate the program. So the next time when the next SIG pipe comes in, this program is going to terminate unless I use signal again to re-establish that I want a handler of this to handle it. And the system does not block delivery of further instances of the signal. System 5, which is one variant of Unix operating systems, also provide these semantics for signals, which is consistent with the original Unix system. And that's not surprising because System 5 is also coming from AT&T Bell Labs. The original Unix also comes from Bell Lab. So it's consistent, because it's within the same organization. This was bad because the signal might be delivered again before the handler has a chance to re-establish itself. Okay? Now, what does it mean?
You get another sig pipe before you call signal again?
Exactly. Okay? So that means there's a window of time where if you get a sig pipe during that time, the program is not going to behave the way it is supposed to or the way you want it to because you didn't get a chance to say that, oh, wait, I don't want this program to terminate on sig pipe. I want to handle this. But you never got a chance to say that. Okay? Now, sig pipe is not a very good example because how do you get a sig pipe? Can you get a sig pipe out of the blue, like just suddenly one day, the program sends you a sig pipe?
No, you have to try to.
You need some sort of file operation to generate a sig pipe, error, a sig pipe, to generate a sig pipe. But what about the other signals, like sig kill, sig stop, and so on and so forth? Those are completely asynchronous. In other words, someone can send you a signal, out of the blue, and if that is happening right between the time after you handle the previous one and before you have a chance to re-specify how you want to handle that signal, then your program is going to go for the default operation, not what you want. Okay, and that's the problem with this particular approach. And based on this description, I'm also assuming that if you try to call signal again within your signal handler, it does not work. Either that does not work, or the resetting back to the default happens before your signal handler gets control. So it's one way or the other, but basically it leaves a window of time where the signal handler will be going back to the default operation, and you have no control over that. BSD, which stands for Berkeley Standard Distribution, which is another variant of Unix, and this one, is it open source? Is BSD considered open source?
There's versions that are.
Sorry?
There's versions that are.
Okay, but FreeBSD obviously is open source.
And that's the primary one.
Okay. But before FreeBSD was out, there were other commercial Unix systems that were based on BSD. Is Solaris BSD or System 5? Nobody knows. Well, these days nobody knows because we are all switching to Linux for the most part. But in the good old days, when Unix was the primary operating system in universities, then people actually remember which one is BSD based and which one is System 5 based. And it's very annoying because they have almost the same commands and almost the same user interface, but they are slightly different. Certain things is different. Okay, BSD improved on this situation by changing the semantics of signal handling, but unfortunately silently changing the semantics when establishing a handler with signal. On BSD, when a signal handler is invoked, the signal disposition is not reset, and further instances of the signal are blocked from being delivered while the handler is executing. Which means if you're in the handler of a signal handler, and when you're inside a particular signal handler, the same signal cannot be generated again. They cannot stack up, basically.
So with BSD, then it didn't do it would reset it to...
It would not reset it to default. But unfortunately, silently changed the semantics when establishing a handler with signal. And that means, I think this part, the unfortunately part, refers to the fact that they changed the meaning of signal without letting people know that they have changed the meaning of signal. So for someone who has been writing, system applications using System 5, when they switch to BSD, the behavior of the program would change. Because maybe occasionally you want to switch back to default. But now it's not. So the program, which relies on the fact that it will switch back to default, would not work in BSD. Because they changed the semantics without letting people know that they have changed the meaning of the signal call. What they should have done is to invent a new call. Let's say signal BSD, signal underscore BSD or whatever. So it's not the same name. Then in the man page, then they can explain how this is different from the normal signal. So anyway, the bottom line is, I probably don't want to go through all of this stuff here, but does everybody get a gist of why we do not want to use signal? Okay, one is you may not get a chance to re-specify signal, but in this class that's not a big concern. But the main reason is your code is not going to be portable across Unix type operating systems. It will only work in some cases, and it won't work in other cases. Any questions? Yep.
In the man page for sig action, it said you can never intercept sig kill using sig action. You can intercept it, but then
It doesn't work.
Yeah,
Right.
it says it'll ignore it and
Correct.
kill it anyway.
Yep. Sig kill is a non-blockable or non-handleable type of signal. Okay, so what we are going to do in this class is we'll continue, but we'll use sig action instead. And I believe my notes has already reflected that when we get to the signal part. Or maybe not. That's just a list of signals. Which is actually the same as this document here. Do you want to read the HTML part or do you want to read the text part? It's the same content. Doesn't matter? Okay. Let's read this one. I think the font is a little bit bigger, it's more readable. Okay, so with this one, it's almost the same thing, except you have 3 parameters instead of 2. And then the other 2 parameters are not a pointer to a function anymore, they are structures. So let's take a look at the first one is easy, okay? It specifies which signal are we talking about. So you still have to pass the same constants, they are integers, like sig kill, sig pipe, sig stop, and so on and so forth. So that part is pretty easy. The second part is, how do you want to handle it now? From now on, how do you want to handle it? And it gives you a third option. The third parameter you can get back how you were handling it before. Now this is kind of big, okay? The difference between this and the original signal is really big because of the third parameter. The third parameter means that now you can stack up signals, or how you want to handle signals. Okay, let's say you want to handle Control C. Control C, I think is it sig int or a sig stop? That's a sig int. Control C is a sig int, which means when you type Control C when the program is running, you're basically telling the program, I want you to stop. That's basically what Control C means when you run the program. But sometimes you may not want the program to stop. The program itself would say, but I'm in the middle of something. I need to write something back to the file before I can exit. Or I'm in the process of writing the file. Instead of correcting the file, I'll finish the entire operation first and then I'll terminate. Okay? So with this particular, with sig action, what you can do is to get back to, you can specify right before writing a file, what you can do is you can call this to set it up with a special handler so they can finish up the entire operation. But at the same time, you can get back how it was handling sig int before. If sig int before was doing something, hey, you can restore back to that point. So that's why you can stack up the handlers, because you can basically say this portion of the program requires this way to handle this interrupt or this type of signals. But this part of the program requires this way to handle the signal, and this part of the program requires this way to handle the signal. So at the end of each part, you can restore back to how it was handled before, and so on and so forth. Is that making any sense? And can you do the same thing with signal before? You can kind of do that, but you need your own data structures to do it. Basically, what you need is a stack data structure in order to store the handlers as you try to specify and stack up the handlers. But that's a lot of extra work, whereas in this way, it is really kind of built into the system call itself. The sig action system call is used to change the action taken by a process on receipt of a particular signal, specific signal, and we can look at the signal list later on. Signum specifies the signal and can be any valid signal except sigkill and sigstop. So sigint is okay. Sigint is Control C. Sigstop is something else, and sigkill is can only be sent by the kill program or by another program. If act is non-null, the new action of the signal signum is installed from act. If old act is non-null, then the previous action is saved in old act. Now that is not entirely correct because it should have said the previous action is saved in the structure pointed to by old act. Okay, because it is passed by pointer, not passed by reference. If it were passed by reference, then this description would be correct. Sig action data structure looks like this. The first one is the handler, and then the sig action, the mask, and the flags, and also the restorer. So it is a lot more complete compared to signal because you're not just specifying one single subroutine to handle the signal. On some architecture, a union is involved. Do not assign to both handler and sig action. Okay, how many people know what a union is in C programming? Nobody. Okay, try it.
All right, it's a struct that has two members of different sizes, but you can only have, I don't know what I mean by have, but you can only have one at a time.
They overlap.
Oh.
Yep. Okay, so basically what happens when you have a union, okay, let me just write it here. I'm kind of surprised that they didn't talk about unions because union is a very tricky feature. It has its applications, but it's usually very, very bad when you have to use unions.
I could never figure out a situation to use it. I did it in a Raj's class where we had a double and an int, just so that you could prove that you knew how to use it. But other than that, I never figured out what was before.
That's about as far as we went.
Okay, so let's go ahead and make a little example out of unions. Okay, so in this union I have int a. Okay, but let's use very specific ints. Okay, int 32t a. We have a character array, so let's call this buffer, and it has 32 bytes. And we also have an integer, a 16-bit integer array. We'll call this C, and it has let's say 100 items. Okay. What this means is I'm going, okay, and then I'll use union u x as a global variable. So the question is, what exactly is x? Does x have all three attributes or just one? But which one? The answer is 1. To answer the first question, x only needs to be large enough to handle the largest member that we have specified. So in this case, A only requires 4 bytes. Okay, so this one is 4 bytes. B requires 32 bytes, and C requires 200 bytes. So that means X itself is going to have 200 bytes as allocated. Then the next question is, but how do we access these different things? Okay, so let's go ahead and write. I'm just going to write a very simple portion of this program, just to illustrate what it's going to do. So let's just say that I'm going to say x.a equals to 0x12345678. Okay. Yep.
I think you're missing the return type for main.
Oh. Is int implied?
No, you do have to include that.
Okay.
You have to, I don't know.
I thought at one point the implied return type was integer.
I've never gotten away with it. The compiler was compliant.
And you're lucky. All right. So the first statement says x.a, which refers to this particular member type, is 0x12345678. So if I want to write this program in this particular way, let's say char, I don't know, I. What if I say I equals to a x dot b bracket 2? What do you think I is going to get?
It's going to get 5.6. Okay. Or 3.4. Or 3.4.
It's using little endian, so it's going to get 3.4. Because this is the same as b bracket 0, this is the same as b bracket 1, and this is the same as b bracket 2. In other words, all of these things are simultaneous. Okay, they're all simultaneous. At the beginning of this union, you can interpret the first 4 bytes as an integer, a 32-bit integer. You can interpret the first 32 bytes as a char. You can also interpret all 200 bytes as 116-bit integers. But for the overlapped portion, you can go either way. That's what a union is. It is only useful in a very small number of situations. One of the situations where it can be very handy is to do something like this. If you want to have your own code to handle, let's say, IEEE floating point numbers, then you can have a union that looks like this. Okay, union f for floating point. Then you can say float f, and then you can use unsigned char b bracket 4. So this way you have individual access to each byte of a 32-bit IEEE floating point number, and you can do all your own manipulation, your own calculation and whatnot, because the bytes are already divided, so it's very easy to access the individual bytes. You can also use typecasting, okay? Because in the situation where you want to break up a 32-bit IEEE floating point number into its individual byte components, you can cast the address of a float into a char pointer first, and then use pointer arithmetic to get to the byte that you want to access, and then dereference it to get that byte back. But this is much more convenient because you don't need like this much typecasting only for this type of only for this much information to get out of it. Okay, that's one situation. The second situation is when you have a much larger structure that only require one or the other interpretation of this space. So it's a space saving feature, because you never really need both at the same time. You just need one. So that way, if you use a union, then you are not wasting space because you're only allocating for only the same space, but it can be used for this or that. And that's the situation that we have with sig action. Because in sig action, you can either use this or that. One is a more general version of the other one. This is what we have been using before. We just specify the handler, and then it takes an integer parameter to specify the signal itself. The other one, takes a little bit more information. It is still a pointer to a function. SA sig action is still a pointer to a function. It takes the signal number itself, but in addition, it also takes some additional pointers so that you can provide more context to the signal handler. Are we doing okay so far with this?
This is acting as a union?
This part is supposed to be a union. And what it says here, on some architectures, a union is involved. In other words, in some unions, the SA handler and the SA sig action part, you can only have one or the other, but not both. It doesn't make sense to have both either. We'll see that in SA flags. Okay, SA restore element is obsolete and should not be used. In other words, this part should never be used anyway. Okay, it's not interpreted even though the field is there. SA handler specifies the action to be associated with signum and may be default for the default action, sig ignore to ignore the signal, or pointer to a signal handling function. The function receives the signal number as its only argument. That's something that we have dealt with already. If SA sig info is specified in SA flags, now that's the part that is important. The SA flags is basically an indicator to tell sig action, how am I supposed to interpret this structure? Should I use sig handler or SA handler, or should I use SA sig action? If this particular constant is specified in SA flags, that means this particular property will be used instead of SA handler. Is that okay so far? And that's why it doesn't make sense to specify both the handler and also the sig action at the same time, because you can either have SA sig info or not. If you have it, then it will use SA underscore sig action. If you do not have it, it will use SA underscore handler. So it makes no sense to specify both at the same time. Okay, just scrolling down here a little bit. This function receives the signal number as its first argument, the same as a normal handler, a pointer to a sig info underscore t as its second argument, and a pointer to uContext underscore t casted to a void pointer as its third argument. Commonly, the handler function does not make use of the third argument. See get context for further information of uContext. SA mask specifies a mask of signals which should be blocked added to the signal mask of the thread in which the signal handler is invoked during execution of the handler itself. Now, let's take a look at this statement here. The question is, when you have a sig pipe and you're inside a sig pipe handler, what happens when someone types Control-C right at that point? Okay. So the question is, you can go one way or the other. Your choices are, we'll go ahead and process, we'll take sig int in this case and process sig int as it is specified. Or two, you just ignore it. You just say that when I'm inside the sig pipe handler, don't bother me. I'm not handling any other signals at this point. If someone presses the Control-C, guess what? You will have to wait until the sig pipe handler is done, then we'll go ahead and handle the sig int. So the question is, which way is proper? It depends on the situation. If your sig pipe or whatever signal you are handling requires a long amount of time, and during that time you are expecting other signals to come in and they are actually significant, then yes, you have to process those signals during that time. On the other hand, if what you're doing inside the signal handler is something that should be atomic, in other words, should not be interrupted, then you can use SA mask to say, I'm not paying attention to other signals or these other signals when I'm in this particular handler. Are we doing okay so far? With the concept, not how to set the mask, just the concept itself. In addition, the signal which trigger the handler will be blocked, and this is automatic unless SA underscore no defer is used. So that means when you're inside, okay, let's say you have your Control-C or sig int handler, but somehow the code that you write inside the sig int handler takes a long time to execute. The question is, what if you type Control-C again when you're still inside a sig int handler?
Blocked.
The normal behavior is it is deferred, which means it is not blocked, it is just deferred. When you're done with the current handler, then the signal will come in again, and then you will go into the signal handler the second time.
It looks like it says blocked, but really it's deferred.
Oh, it is blocked unless it is deferred. Oh, okay, you're right. So by default, it is blocked.
What is it? Okay, so no defer when it.
If you specify no defer, that means they can stack up. So when you're inside, the sig int handler and you type Control-C again, if you specify no defer, that means the signal handler will be invoked on top of itself. It's kind of like recursion, because
Okay.
you have a subroutine running, and then you have a trigger to cause the same subroutine to run
So stop
again.
where it is and start another subroutine. If you do the no defer.
Correct. But when the second subroutine or the second invocation of the handler is done, it will go back to the first invocation of the handler to finish the rest of it, which can cause a lot of problems depending on what you're doing in the handler. So the usual operation, the usual way of handling it, which is blocking it, is the proper way to handle it. A lot of these concepts also apply to hardware interrupts. In other words, if you get a hardware interrupt, let's say from your hard drive controller, your SATA controller, saying that, okay, I'm done, transferring all the bytes, to this particular hard drive. Is there anything else for me to do? It's going to cause an interrupt. An interrupt is basically a signal, except it is generated by hardware. So inside the subroutine, and you're setting up and say that, oh yeah, we got a lot more stuff to transfer to the hard drive, and this is the buffer, this is how I want to set up the DMA channels, and so on and so forth. What if, right at that point, your NIC card says, hey, I got another packet too, I need some attention from the processor. How are we going to handle it?
You gotta block it.
Well, the normal operation on most architecture is blocking the new interrupt. In other words, it's not ignoring it, it's just blocking it for the time being. It's basically saying, well, we're going to finish handling the hard drive interrupt first, and then when the hard drive interrupt is done, it will return back to normal execution. As soon as interrupt is re-enabled, then it will get the interrupt from the NIC card, and then the operating system will handle the NIC interrupt. And that's the usual operation. In other words, normally you do not want to use no defer. I mean, no defer really can cause a lot of problems.
So no defer would also handle, it's not just handling the call of, if you were handling a control C or a SIGINT signal, it wouldn't, the no defer isn't just for another SIGINT.
It specifies from now on, SIGINT can stack up basically.
But would it allow? Does that also have to do with other signals?
No, it only applies to the signal that you're dealing with, because sig action as a function requires the first parameter to specify which signal are we talking about. So when you specify SA_no defer, you're only applying that to the signal that you are specifying. It does not affect the other signals. And the SA flags, it specifies a set of flags which modify the behavior of the signal, and it should be a bitwise OR. Basically, you take all of these constants, pick out whichever one you want to use, and then use a bitwise OR to OR all of these things together. Because each one is basically just using several bits to specify, that particular option. We haven't really talked about child processes yet, so most of the discussion at this point, we can basically stop here at this point. Yep.
So the mask one, okay. So let's say mask is that also that's also used to, is that what the that's also used to specify what other signals are processed, right?
So most of the time you want to say no. You want to say, I'm not going to process any other signals during this time. No defer applies to the signal itself, right? And can I have another SIGINT when I'm in a SIGINT handler? The mask applies to everybody else.
Okay, so you'd also do the bitwise OR for the same mask?
I think sig mask is really just a bit mask. In other words, bit 0 corresponds to signal 0. Bit 1 corresponds to bit 1 corresponds to signal 1, and so on. So SIGQ is going to be bit 9, which is also 512. So you have to do all the bitwise OR with all the signals that you want to specify in mask. Any questions at this point about sig action?
So you don't want us to use signal, you want us to use sig action?
You can use signal, but only when you want to go back to the default way of handling things, and also when you want to ignore a particular signal. In your homework assignment in socket 3, because we only want to ignore sigpipe, so that will be fine.
Okay.
Yep. And we don't need to restore anything. If you need to save something and then restore it later, you should also use sig action instead of signal, because signal doesn't give you back how it was handled before, whereas sig action does. Okay. Any other questions? We're not going to go too deep into sig action and signals in this class, because at this point we can't, because we haven't really talked about child processes and multi-threading yet. So we have to kind of go through some of those topics before we can really use sig action. Any questions at this point? Any questions? If there are no questions, we're going to start on a new. Where is it? right here. We'll start to talk about multiprogramming in Unix, which is a very interesting topic. How many people still remember the discussion of having a single thread, single process program to handle multiple connections, basically Squid? You remember that? Okay, what is Squid from our previous discussion? How many people still kind of vaguely remember what Squid does? Yep.
It's essentially a caching proxy that will sit between a client and server that are trying to communicate, and will potentially multiple clients or what have you, and will basically figure out how to more efficiently deal with getting the data from server to clients.
Exactly. It's an optimizer. Yeah. It's basically an optimizer. So let's say I am the gateway. From everything from inside the Los Rios network has to go through me to go to the actual outside internet. Okay, so I'm the gateway. But if I am also a proxy server, a caching proxy server, then I can do a lot of tricky stuff to minimize the bandwidth that I require, with my outgoing traffic. Because if this entire class want to download the same 16 gigabyte file, I only have to get 16 gigabytes once from the actual source. But once I have the 16 gig file sitting on my cache, in my cache, every single one of you who want to get to that particular URL, address, I'll just feed it to you. And I say, I have a local copy. You don't have to go out to the internet anymore. I have a local copy, and I'll just feed that to you. And that way, my outgoing traffic to the actual internet is going to be optimized, because I still need to get it once, but that's the only time I need to get it. Okay, that's what a proxy server does, or one of the many things that a proxy server can do. Now, what is the challenge of Squid being a single thread, single process program?
Gotta keep track of where it is for everybody.
Exactly. Okay, so that means, let's say this entire class are clients, okay, web clients that wants to go through me to get out to the internet. So this means, when you are making a request, he can be making a request at the same time, and at the same time, I may be answering your request. I'm feeding you, the 16 gig file already, and you want to do something else. So I have to handle all these different requests, and all these different requests, all these different connections can be at a different stage of the connection, also. So I have to be responsible to track every single thing. How does that impact the writing of the code? How do we handle a protocol, like HTTP or whatever protocol you want to handle? Well, you typically want to do it in a sequential type of program, right? Okay, the first part of the program is going to handle the header. Okay, the second part will handle maybe the options and so on. Depending on how the protocol is specified, you just want to process the protocol sequentially as it is specified in the specification, right? But I can't do that anymore, can I? Because when you send me your HTTP request, let's say an HTTP request can be this long, okay? But you may be sending me that request in very small chunks, okay? It may be your computer being slow. It could be a whole variety of reasons. So as you are slowly transmitting, the HTTP request to me, I need to answer back to her because she wants that 16 gigabyte file, and I have the entire file here. I can basically saturate the pipe and send it back to her as quickly as I can. So what is going to happen now? You're sending me the request very slowly, and I have to send back a 16 gig file back to another client as quickly as I can. Well, we have to use select, right? Sure. That's the whole reason why we are talking about the select call, is so that we can use a single process to do it. But select is nothing more than an engine block in this whole thing. The next question is, but how do I write the program to do this? I can only tell you, if I want to describe Squid in one word, it's obscure. Okay, it's a very difficult program to read. Okay, if it is the first time that you read this program, you will have a very hard time understanding the program. Even the organization of the program is really hard to understand, because every instance of communication cannot be specified by a single subroutine anymore. What you normally use a single subroutine to specify, like how to handle the HTTP header of the request, can now has to be broken up into multiple portions. Because every time I have a select to unblock, I can only process a little bit, as much as I can, just a little bit. If it is beyond a point where I can do some processing, I just stick into a buffer until I get to the point where, oh, okay, I got enough stuff, I can actually do something about it. Yep.
So is this the kind of thing that's going on behind the scenes in event-driven languages?
In a
Event-driven languages?
event-driven? Yes, it is very much the same thing, except in this case, the event, the so-called event, is the availability of bytes or content, but it is event-driven. It is event-driven, and that's a very good comparison. So that makes the program extremely hard to write, extremely hard to debug as well, because the code is no longer sequential. What logically follows from this step to this step, you cannot put it into the same subroutine anymore. You have to put every single chunk into a different subroutine, and then each connection has to maintain its own state so that it knows, oh, when we come back and the select call unblocks and I have something to do, this was where I left off last time. And then you continue the processing that way. So that means you will see a lot of nested switch statements, which is typically how state machines are done. And that makes the program not very easy to understand. I have the honor of doing that back in 2004. No, 2000. It was 2001 or 2002, and it was a challenging program to read. Okay, so but it does have one advantage. What advantage does it have? Efficiency and portability, because it only relies on select. And select is available and it's implemented pretty much the same way across Unix, Linux, and even NTFS. Not NTFS, Windows NT. The NT kernel has a select call as well, and it does about the same thing as all the other select calls. So that means I write a program once, I can recompile it to any platform, which is nice. But it does make the program very hard to maintain. And that's why we have this discussion, because one thing we can do is to have processes. What exactly is a process? We talked about that in this class as well.
Program in execution.
A program in execution is an instance of a program. It's an object. Okay. If you look at a program as a class, it is just sitting on the disk. It describes how a program should do when it's being run, but it's not actually doing anything on the hard drive. When you run a program, it becomes a process by an object, and it is actually doing something at that time. So that's the difference between a program and a process. So here's the opposite spectrum of the entire thing. Squid is on one end of the spectrum, and then a lot of FTP server programs are on the opposite spectrum. Okay? So let's just say that I'm inventing a new protocol, okay? Protocol X, whatever it is. And I just want to test it. What is the best way to test a program of how it is handling a particular protocol? Standard in, standard out, right? You give it standard in as a test case, it will give you back standard out as a result, and if you are only testing something that is static, you can debug the program pretty easily. Is everybody understanding what I'm saying? Yeah? Okay, let's say it's FTP, okay, or file transfer protocol. Okay, it's pretty easy to test, if you just want to test, whether it is working correctly, because what you can do is you can specify in standard in a request to a particular file. So the standard out, only has to respond correctly, grab the file, and respond to you correctly, and you can automate the test for the most part in this case. Standard in, coming in, parse the protocol, parse the communication, respond to it, send back a file, you're done. Okay. But what is so special about standard in and standard out? A program that is using standard in and standard out can only do one connection at a time. Is that making any sense? How many standard ins do you have? One. It's file descriptor 0. How many standard outs do you have? One. It is file descriptor 1. So if you write a program to handle a protocol by using standard in and standard out, you can only handle one connection at a time. Is that making any sense? So that means every connection is only handled by a single process. Okay, that's the other extreme. And you can do it, have I talked about the concept of a super server in this class?
Yes.
Yeah? Vaguely? Okay.
Maybe I missed one class. Something.
Okay. The concept of a super server is basically a pimp. Okay? It's the middleman to do everything else. So let's just say that this half of the class are clients somewhere on the internet, and this half of the class are servers that I can run on the particular machine. But each one of you is a program that only uses standard in and standard out to handle one single connection. Is that okay so far? Okay. So let's say both of you want to do file transfer, using FTP, and I'm called the super server. The super server's job is very simple. I'm the middleman. I handle all the setup of the connections, the sockets, and whatnot, but I don't handle the protocols. Okay. So when you say that you want to transfer a file, you open up a connection, I get a connection from you. And that's a socket connection over the internet. But then what I would do to turn around, I would just say that, okay, well, I don't understand FTP, but you do. Okay, so I'm going to ask you to start a new instance, to start on a process, and your process, that particular process, your socket coming into me will be my standard out to you, that will be your standard in. Your standard out from your perspective, going back to me, is going to be your socket incoming traffic from your socket. So I'm just passing things around. I'm the bidirectional pump and no more than that once the connection is established. Let's say you want to do a FTP2 while this connection is going. No problem. Okay, I'll accept your socket connection. Your socket coming into me is going to be my standard out to a second instance of you. I started a second process just to handle the second connection. So if anybody else wants to open a new FTP connection, that's exactly what I would do. Okay? So every connection has one process corresponding to it. That makes programming very easy, doesn't it? It makes testing very easy. Because now if you want to test your program, okay, I'm not quite sure my FTP program is handling the protocol correctly. Well, guess what? FTP is a very easy protocol to test because the protocol itself is plain text. In other words, you can actually just type up all the commands, using the protocol of FTP and see how an FTP server is responding to you. So it's very easy to test because it's just standard in and standard out. In other words, I can test the FTP program just by typing in something, reading the standard out, typing something in some more, reading the standard out, and I can debug my program that way. So, and the program itself can be very sequential because it is just a single thread, single process program. What is the downside of this approach? If I have 5,000 connections all going on at the same time, how many processes do we have? 5,000 processes. Okay. But someone's going to argue, but if I have 5,000 connections through a proxy server, through Squid, I still have 5,000 connections. What is the big deal of your 5,000 processes versus one process, one thread that has to handle 5,000 connections? What is the big deal? Is there a difference?
Overhead, I guess. Overhead?
The overhead, very good. What type of overhead are we talking about here? What has to be replicated from one process to the next? The stack, the heap, okay? Now the program space is something different because in Unix and many other operating systems, different processes can share the same code space in the program, in the memory space itself. So that part doesn't have to be replicated. But the stack has to be replicated. The heap has to be replicated. The static area of a program has to be replicated. Okay? So that means if I use 5,000 processes to handle 5,000 connections, I'll be using significantly more system resources as opposed to a single thread to handle 5,000 connections.